So, my talk is connected to the notion of mean derivatives, and the main purpose to find some conditions under which first of all, this equation generates a stochastic flow where every solution is called orbit, and we will find the conditions under which all orbits exist on the whole half line. Previously, a new point here is that this equation is given in terms of forward mean derivatives. We will give a definition below. And previously, we considered them generated by the so-called current velocities. It's symmetric mean derivatives. Please note, these are two different problems with different methods of investigations and different applications. And it is supported, this research, by Russian Science Foundation. Yeah, you see, I have to mention this. Some facts from the theory of matter. Yes, and second, this equation is so-called excuse me, algebraic differential. This means that its phase space is constructed by two different sets, on which, on the first one, the equation has one form, stochastic, and on the second, it's another form. On the second, it's in fact algebraic. Yes. Now, to start, we have to have some facts from the theory of matrices. If we have two n multiplied by n constant matrices, M and L, where M is L is degenerate and M is non-degenerate. The expression lambda L plus M, where L is a real parameter, is called the matrix pencil. The polynomial, this, is called the characteristic polynomial of the pencil. The pencil is called regular if its characteristic polynomial is not identically equal to 0. We shall deal with regular pencils. Then we can apply the so-called Kronecker-Weierstrass transformation and reduce its matrices to the so-called canonical quasi-diagonal form. In the canonical quasi-diagonal form, under appropriate numeration of basis vectors, in the matrix L, first along diagonal, there are Jordan boxes with zeros along the diagonal, and the last matrix along the diagonal is the unit one. But for M, we have another structure. In M, the lines corresponding to Jordan boxes, there is the unit matrix, and the last block at the bottom is a certain non-degenerate matrix. Everywhere below, we will deal with regular matrix pencil, as I said above. Now, consider a positive definite and non-degenerate D multiplied by D matrix. This is my favorite Greek letter called capital Xi. Yes, Xi of T. Lemma, there exists a matrix of the same range, A T, such that Xi equals A multiplied with A conjugate. This means it's transposed A. Now, preliminaries of mean derivatives. Consider stochastic process in Rn given in a certain probability space such that psi of t, small psi, and is L1 random variable for all t. Every stochastic process in Rn determines three families of sigma subalgebras of sigma algebra F. It's they call the past. It's generated by preimages of Borel sets in Rn by all mappings psi of S for S between 0 and t. Then future, the same, but for simplicity, we will deal with a process given on a finite interval from 0 to t capital. The same, but for S between t and t capital, and the present. It should be denoted by p as well, but it's not good. And the author of this theory, Edward Elson, decided to use letter n from now. It's very simple. It's generated by preimages of Borel sets by the mapping psi of t for this t itself. This now present is very important for us. All families supposed to be complete, containing all sets of probability 0. For convenience, we denote the conditional expectation by the present, like this. And in unconditional expectation is E capital simply. Now, of course, everybody knows that for normal in common sense stochastic process, all its trajectories, sample trajectories, are not differentiable. And Nelson suggested what to do in this situation. We don't want to use generalized functions and give the definitions as follows. It's forward mean derivative. You see, it's practically the same definition as for ordinary derivative, but here we have conditional expectations with respect to the present. The limit is supposed to exist in L1, and this means that it tends to 0, and it's greater than 0, as usual. This is the definition of backward mean derivative. Everything is the same. But here we you see psi minus psi of t minus delta t instead of psi of delta t plus delta t minus psi of t. The same, and we will use also the derivative that is half sum of forward and backward mean derivatives. It's called symmetric mean derivative, and the vector is called current velocity. It should be mentioned that current velocity is a natural analog of ordinary physical velocity of deterministic processes. We introduced the next mean derivative that we call quadratic. You see, it is forward-man derivative multiplied with its conjugate. So we have column on the left and row on the right. This product is a matrix, but when we go to the limit, we obtain some good formulas for example, for such an iterative process, its forward-man derivative is the shift, and quadratic-man derivative is diffusion coefficient. In spite of the fact that matrix is of rank 1. But when some summons tends to 0, we obtain these formulas. Now, for a Wiener process, we can calculate everything. First of all, since it is a martingale, one can easily see that its forward-man derivative equals 0. But for backward-man derivative, we can prove the following formula. Backward-man derivative, you see, W over T. And current velocity then equals W over 2T. And now we are in position to deal with the main result. Let Xi be continuous, symmetric, positive, definite. D multiplied D matrix. By lemma 1, it was above. There exists D multiplied D matrix A, such that Xi is a multiplication of A with A conjugate. It can be called square root of Xi. Now construct n matrix theta in this form. Our Xi and zeros around. Now we consider the following stochastic algebraic differential system. All matrices here are in canonical quasi-diagonal form. L forward-man derivative eta equals to m eta plus a continuous deterministic signal. Physical interpretation. It describes some electronic device. F is incoming signal, and eta is stochastic outgoing signal. The quadratic mean derivatives is our theta. Let M and R are given in canonical form. I have said it. F at T is a smooth deterministic vector in Rn. Taking account the structure of matrices Ln, we see that system 5 is decomposed into several independent systems. The one in upper left corner with the unit matrix in L and matrix J in M, and the system corresponding to Jordan boxes in L and the unit matrices in M. And we can consider every system separately. They are independent. The system in upper left corner takes this form, and where eta sub 1 and f sub 1 are constructed from the first d coordinates of eta and f, respectively. It's an example of that Jordan matrix. Now we have an example of the blocks with gender matrices in L and the unit matrices in M. We consider P multiplied P matrix, Jordan box, and in the following form, and the corresponding unit matrix from M. Then the other systems with Jordan boxes are quite analogous. This system takes the form. You remember in theta, only in left upper corner, there is our xi, and all other elements are 0. That's why here we have 0. These vectors are constructed from the last p coordinates of the corresponding vectors. Let the greatest Jordan box in L be Q by Q matrix. We investigate the class of systems 5. It is, you remember, it's for Jordan boxes, satisfying the following condition. The vector f at t is uniformly bounded for t on the whole half-line, together with its derivatives from the first order derivative up to the nth order derivative. It's evident that the solution of 5 under this condition exists for all t on half-line, if and only if the same is valid for solutions of 6 and of 7. We will start with 7. For this condition, I included for simplicity. In fact, I don't want to discuss global existence of ordinary differential solutions for ordinary differential equations, in spite of the fact that I have necessary and sufficient condition for it. But it will take much time, and it's better to use this condition for simplicity. So we start with 7. Theorem. If equation 5 satisfies condition, the solutions of 7 exist for all t. Excuse me, my system was crushed not long ago. And after that, when my LaTeX system in formulas does not write Latin letters. I have to put them individually, and sometimes I miss it. Here should be T. Sorry. Somewhere below, I found here analogous situations as well. So now we return to 6. Here we'll find several conditions under which the flow generated by 6 is complete. This means the solution of 6 exists for t. Now I didn't miss it. On the whole half-line. Definition. The flow xi of s is complete on 0t capital if every orbit, this means the individual solution with given initial value, almost surely exists for any couple tx with t between 0 and t capital, and for all s between t and t capital. The flow is complete if it is complete on any interval 0 t capital. The structure of equation 6 means that its solution satisfies the following stochastic differential equation in eta form. You see? Here should be ds, is ds, sorry, where A is such that A conjugate is Xi. There's a generator, it's very important for us, of this equation. It can be found explicitly by this formula, where sigma up ij are the elements of matrix Xi. These are elements of matrix J, and F are the coordinates of vector. Here should be coordinates, sorry. The backward equation takes this form, and you can find the backward generator by this form with the same problem, where trace is the derivative of f along the vector field, this one. Definition: a function from a topological space X to the real line is called proper if the preimage of every relatively compact set in R is relatively compact in X. Let there exist a smooth proper function phi on R such that it's, you remember, it's the generator applied to this phi is uniformly bounded by some constant C for all t and x. Then the flow psi ts is complete. But it is very far from a necessary and sufficient condition. It's only sufficient condition. To obtain necessary and sufficient or something close, we have to come to generalized first space, Rn multiplied with R. Consider this multiplication and the flow psi with tilde in this set with the generator. This is the generator that we deal above, and d over dt, it is a part of generator in R. Let there exist phi tilde such that the same as above, analogous as above, and t. Then the flow psi of s on Rn is complete. You see, it's a very simple corollary. We we deal with new flow, and obviously obtain the same result for flow we deal with. But it gives a result close to necessary and sufficient. We say that the flow is continuous at infinity if for any finite interval, any t from it and any compact k in Rn, the equality, you see, holds. This notion was introduced by Laurent Schwartz, and it is very important for us. You see, probability of the fact that the orbit, psi of tx, at finite element of our interval belongs to k, probability that this random element belongs to k equals 0, as x goes to infinity. It means that from infinity we cannot get into any compact set. Starting in infinity, you should understand in common sense, of course. Yes. Let a flow is having smooth, strictly elliptic generator and being continuous at infinity is complete on 0t if and only if there is a positive proper function ut on this multiplication. Remember, it's a line and it's our to our that is C1 smooth in t and C2 smooth in x, and such that that generator on that multiplication spaces applied to ut is bounded by a certain constant c, positive, at all points. You see, now we obtain necessary and sufficient conditions, but not for all. All processes, all equations, but those that satisfy infinity, continuous in infinity. Yes. Two words. The necessary and sufficient condition for ordinary differential equation is of the same type, but for ordinary differential equations, the solutions satisfy continuity at infinity. It should not suppose additionally. I told about it earlier. And the situation, if backward flow is complete, the forward flow is continuous at infinity, and vice versa. Next, the last situation. Now consider both generators, forward and backward, and suppose that for them we obtain such inequalities. Then they both continuous at infinity, and for both of them we obtain necessary and sufficient condition for completeness. Thank you for your attention.